Yeah, exactly. It's a matter of cost, it's a matter of time, and it's a matter also of the performance that a programmable photonic device enables. So beyond the prototyping or fast development, we at iPRONICS certainly believe that there is something else beyond these benefits.
Hello, everyone, and welcome to the Altium On Track podcast. I'm your host, Zach Peterson. Today, we're talking with Daniel Pérez López, co-founder and CTO of iPRONICS. This is an interesting area that is, of course, a passion of mine. Today, we'll be talking about photonics and specifically programmable photonic chips. Daniel, thank you so much for joining us today.
Thank you. It's a pleasure.
Yes. Those folks that know me or that have watched the show or any of my other videos for a while know that I came from optics and then went into electronics. And what you do, I think, is a little bit of a fusion between optics and electronics. So maybe tell us what iPRONICS does, what your product is.
Perfect. So yeah, I think that just to explain the concept, when we refer to programmable photonics, we are referring to the ability of first being able to integrate light signals into a semiconductor chip. That is widely known as integrated photonics, integrated optics. It's the field that allows us to have transceivers for internet connections, for data centers, and so on. But when we add the keyword programmable, we are referring to something else, which is the expansion of the field to provide the ability to program light-based signals. So just to give a specific example, a photonic integrated circuit today and during the last, I would say, 20 years, looks like a chip where we integrate waveguides rather than wires. So we are able to integrate optical signals, get them into an optical chip, and we are able to perform some kind of processing within this photonic integrated circuit. But what we are enabling is the programmability of this signal. So there is a parallelism that we can use here, which is a field programmable gate array, a programmable logic device in electronics versus an application specific integrated circuit in electronics. So iPRONICS will be providing this programmable FPGA like homolog, but in this case with photonic integrated circuit rather than with electronics.
So I think this implies that most photonic integrated circuits up until now were static, essentially like ASICs, like you say.
Correct. So as I mentioned, the photonic field or the integrated photonic field, it's mainly limited to two key volume-driven market segments that are transceivers and data centers. So the generation of equipment, circuitry that allows us to move data in the optical networks and within the data centers. But the technology has been maturing during the last 30 years and has been demonstrated being competitive with among different application fields, from LiDAR to optical processing in other fields, like, for example, quantum photonics or more classic-oriented operations. It's also well known, for example, that you can use RF signal processing, generation, and detection with assisted by photonic integrated circuits, and there is also an opportunity there for integration of these kind of systems and components. However, since we are all constrained or the technology is constrained to application specific designs, then the time to market, time for development, it's really high. And there are only a few of companies that can actually invest on these kinds of long iteration cycles. However, the addition of a programmable photonic device, in the same way that it happens with the FPGAs in electronics, it's an opportunity to reduce drastically these time for development times and also the overall cost related to the development of a photonic integrated based product.
I see. So the market really needs a programmable solution, simply due to, I guess, the limited size of the market for, especially for like ASICs. Either the processing and fabrication costs come way down for all those application specific photonics, or you have to have a programmable solution in order to get it out to market.
Yeah, yeah, exactly. It's a matter of cost, it's a matter of time, and it's a matter also of the performance that a programmable photonic device enables. So beyond the prototyping or fast development, we at iPRONICS certainly believe that there is something else beyond these benefits. For example, just to put some concrete applications, if you think about, let's say, for example, a front end RF system that demands some kind of adaptability, tunability, flexibility. If you are thinking about next generation 5G, 6G base stations, there is a high demand on adaptability and being able to reconfigure your system on real time based on the specific environmental conditions or based on specific performance that you need to get at one time or at another. So programmable photonics, it's going even beyond cost and time for development reduction. It's also about key performance that will enable next generation communication systems or processors.
So, speaking of next generation processors, one area where I repeatedly see that type of processor come up, whether it's a quantum processor or a photonic processor or a quantum photonic processor, is AI processing. So, specialized chips that could go into the data center that can interface directly with an optical link between servers, and then they have very high compute and they can process all of this data for AI. Is
Mhm.
that the type of market you're targeting? Or are you targeting maybe smaller devices that need high compute, that can benefit from this type of solution versus, say, an FPGA, a small processor, for a variety of reasons?
Mhm. Yeah, that's certainly a good question. There are many companies in the field now today that most of them were born like in the last, I would say, decade or even 5 years that are pursuing this race for photonic AI hardware, photonic AI software. Um, there is a discussion within the community and both industry, academia, where everyone is trying to analyze what is the real benefit of photonic technology. As you mentioned, it's direct substitution of what we perform nowadays by digital means. It's cooperative technology that allows us to complement where electronics it's not able to deliver. We certainly believe that photonics technology is a complementary technology to electronics. It's in most cases or on a specific application cases, it's no sense to try to substitute technology that is already performing well for a specific functionality. So rather than reinventing the wheel for something that works, actually people, practitioners, programmable photonics photonics engineers, designers, and companies should be targeting what is actually producing the next generation performance in terms of, for example, you mentioned AI. With the AI, you can try to target the multiply and accumulate directly in the photonic domain, or you can try to focus on the interconnects, the data movement between the different resources, GPUs, and other subsystems in computing clusters, for example. Is an open discussion that is today in the community. From iPRONICS, what we are focused on our first 3 years has been being able to deliver something tangible to our customers. I think that we are one of the few companies that is actually serving products to customers nowadays rather than trying to invent the future. So we are already delivering in the present, and that allows us to receive direct feedback from companies, our customers, working on many different fields. Some of them in communications, some of them in pure signal processing, some of them in RF photonics signal processing. And some of them even in computing. So we are very close to all these markets and getting feedback from them and working on our next generation products already based on this feedback.
So when you say someone's going to use one of your systems, right, or one of your products, um, I think when someone hears photonic integrated circuit, they're going to try and put this into, let's say, a PCB or put it into an electronics assembly, and they're going to say, well, how do I get an optical interface into the chip? How do I get signals into the chip? Is there an electrical interface or is it all optical?
That's a great question. So our photonic processors today looks like a rack system where we have embedded all unit there. So basically, all the control electronics that are required to drive the processor. We have all the optical interfaces. We have some kind of logic within the device. We have, in summary, the photonic layer, the electronic layer, and the software layer on top of everything. So what we are enabling our users, and we recognize that, and we are also measuring it, like some of them had a strong background in physics, photonics, and optical equipment in general. Some of them has had never heard about photonics, so they want to use the system as a black box. In this case, what we have done is develop a software development kit that allows our programmable photonic developers, customers, users to use the technology without the need of being experts in the field. So if they have a general programming background, they can use our libraries, software development kits to program the optical interconnects, optical switches, optical beam splitters. So they are able to tune the amplitude and the phase of the light if they want to get at that level, but at the same time, if they just want to keep high on a system level perspective, I just want an optical switch router or an optical filter. They just put the specifications and the system gets programmed for them. From interaction perspective, you can get your signals in and out by means of optical fiber connectors. So we have worked on specific interfaces to connect these optical fibers with the photonic integrated circuits with a fiber array. And you also ask about the interfaces. We are already developing a system that allows you to program RF signals as well. So being able to mix RF high-speed signals together with optical signals. So in that sense, the interfaces looks like RF connectors, fiber arrays, and then a communication port to communicate with the logic of the device.
So with this being a rack system, I think that makes sense for the data center environment where everything is in racks, right? That makes sense. Another area where it makes sense is like, military embedded, right? They'll go out in the field, they'll set up racks and do basically the same thing as a data center, just smaller scale.
Mhm.
And I'm sure we can come up with some other examples. Um, Now, with it being a rack system, of course, it's very large, not portable, unless you're going to roll around a rack with a portable power supply.
Yeah.
Um, how do you take that and then maybe scale it down and eventually bring this kind of technology to smaller devices that don't have to be rack mounted? Is that possible? Is that something you have on the roadmap?
Yeah,
What do you think about that possibility?
yeah, it's certainly the question. Um, I mentioned before that probably we are one of the few companies in the market that has been able to deliver something, and that has been our decision making process, our motto all the time, being able to put this in the market as early as possible, so our users, customers can actually enjoy the technology sooner than later. It's better to have something rack based in 2022 rather than waiting for 2026 to have something with a smaller form factor. So we basically decided that that was the way to go. And that being said, we already have worked on the miniaturization of the device. Um, on most of the issues, or well, most of the issues, the challenges that comes together with form factor reduction has been already mitigated from our side. Our next generations are going to be smaller and smaller still being able to reach fundamental limits. That I don't think that the fundamental limits are nearby in the future. As you mentioned, being able to miniaturize the device 2x per year, it's not something crazy. And as you mentioned, we really believe that reducing the form factor is also a way to open doors to additional market segments. Today, rack-based equipment allows you to be in laboratories, in universities, in companies, in data centers, but miniaturizing the form factor for sure allows you to democratize even more the technology. So yeah, that's totally in alignment with the company.
Yeah, there's one joke I often make about quantum, which is that it would be really great if we could have like a quantum iPhone, right? But you have to take all of that, cooling system and the chip itself and miniaturize it to iPhone form factor. So this, of course, makes me wonder if one day we'll have photonic iPhone or
Mhm.
photonic Galaxy if you're a Samsung user.
Yeah, probably that's aligned with one of my previous comments. It's trying to reinvent what is already working very nice. Like, for example, why? Then the question would be, why do we need a photonic smartphone? Is what what type of problem are we trying to solve? Of course, today we have displays, which is photonics technology for the screen. Some of the mobile phones has photonic based sensors, but if we are referring to photonic smartphone as something that totally replace the processor by a pure photonic processor, I don't think that we have that need today. So what we are focusing now is on again hearing the market, what are the actual needs. So far, no one has asked for a photonic based phone, so we are trying to focus on as you mentioned, getting better form factors, improving the technology overall, and enabling the next generation. For example, I think since you mentioned phones, one area that we believe that for programmable photonics is of great interest is next generation 5G, 6G communication stations. We really believe that the adaptability, the flexibility that is demanded by the new protocols, and also having a system that you need like 2 years to upgrade from a hardware perspective, do not go well with something that is asked to be extremely flexible, upgradable from next generation protocol to the next generation protocol, having the possibility of just software update your hardware, and that's only possible with programmable photonics.
Well, you brought up the analog to an FPGA with programmable photonics, right? So I guess someone might rightfully ask, well, why would an FPGA fail in that kind of application? Why does a programmable photonic chip have the advantage?
Yep, yep. So that's a great question. Then we get into the territory of comparing the benefits of photonics versus electronics directly, not versus other photonics approaches. And to that question, then where photonics excel, it's in a wide variety of areas. Like for example, if you are using photonics for assisting RF systems, photonics allows you to provide flexibility. Like for example, being able to create a reconfigurable filter that is able to work with signals at, let's say, 28 gigahertz, 37 gigahertz, 10 gigahertz, 5 gigahertz. Being able to do that in a reconfigurable way with RF systems is a real challenge. So being able to have an RF filter that you can filter in the RF domain directly or RF dash electronic domain, being able to reconfigure the bandwidth and at the same time the central frequency is a challenge for current RF systems today. That's something that potentially photonics can help. Why? Because you are using a modulator, you get your signal from the RF domain to the photonic domain, where you have all the flexibility that you need, and then you can get back to the RF or millimeter wave domain to have your signal converted and processed. Similarly, you may want to have fiber to the antenna connections, and then in that case, your interface is already optical. So if you want to solve that with an electronic FPGA or an electronic engine, you need to down convert your optical signal to domain before doing any kind of processing. If you have the signal that is coming already in the optical domain, you can benefit from that and perform some processing there with massive reconfigurability. If you are based on fiber rather than on in electronics wiring, you can also benefit from low loss distribution loss, and then you can distribute your signal among different fibers and areas. Of course, this conversation depends on the applications that we are focusing. In this case, we are talking about like opportunities for future base stations and 5G, 6G communications, but the same will go with other applications too.
So you're currently developing a box, basically. I think you described it as a black box to some people that you can purchase off the shelf and then plug into and start using. However, if you dig into that box, of course, you'll find all these different components. I'm sure most of them are off the shelf, aside from, of course, your processor. So I'm now wondering, is there ever going to be an opportunity for someone to, let's say, just purchase one of your processors, buy the other components around it needed to run the processor optically just off the shelf, and maybe build a custom system around your products?
Yeah, so the first generation processor that we have put in the market is basically being a rack size module. It's difficult to co-integrate with others products. So this allows and is allowing the some of the tier one telecom operators, for example, in the world, to start working ahead of the possibilities of the technology. Uh, Even though it's not yet integrable in or with a form factor that allows them to integrate that into other products, it can be, as you mentioned, unless you are in a data center or similar. This allows them to start kicking off the learning process of programmable photonics. It's a really fast learning process, but they are already working on generation of functions, their custom algorithms on top of the base algorithms that we provide. But totally agree with what you mentioned. What we are developing is next generation boards based equipment, so it's easier to integrate a board within with different components. So rather than them thinking about the control electronics and everything else, the board size device will incorporate already the photonic integrated circuits, the necessary control electronics, the necessary logic. So then you only need to worry about what matters for your product. Like if you have, for example, let's say that you are developing an intra-data center orchestration system where you want to have a smart router connecting beam splitters, optical interconnects, then you will focus on the optical interfaces and the communication interface. You don't need to develop anything else. We have optimized already the control electronics to get a fast reconfiguration time, to get all the synchronization among the software layer, so you as a user can focus on what you can actually provide value.
Well, I understand that, and I get that, getting this first generation product out to market is really important, especially for maybe developers who want to build on top of this. I guess I'm just wondering if there would ever be an opportunity to release something that's in like module form factor, so that it has the integration that you're describing with all the control electronics built around the chip. It has the optical interfaces somewhere on the module, and then people still interface to it on a custom system, but I think having the optical modules around, or the optical interfaces, I should say, on that module make it a bit more challenging, because usually in the electronic space, when we think about like a module, we think about something that like plugs into a couple of board-to-board connectors and it's all electrical. And then we don't really worry about it. But then when you add the optical element to it, I think people then wonder, well, how would I interface to that kind of module in order to take advantage of this, especially if my application isn't going to be best served with a rack mount unit.
Mhm, mhm. Yeah, to that point, if you think about a board size system where you have a photonic integrated circuit, your control electronics, and your peripherals, or let's say connectors or ports. Um, if you have a not a development board, but a board that can integrate within a product, and the product demands optical interconnections, then it will depend on the volumes that we are talking. So for specific volumes that are high enough, it's possible for us to just interchange the different connectors and adapt the final connectors to the users. Otherwise, complete development board with the specific MTP connectors having within a single connector, you can just plug more than 24, 34, 64 optical fibers within a single connector. So from an optical connectivity perspective, I think that it's a good example. Today, the opposite to that is either, of course, non-integrated table-based components aggregation based on discrete components. So you can have your modulator, you can have your photodetector, you can have um, components that basically consumes or takes some centimeters by centimeters when all distributed all together. And the beauty of our integrated device is that most of these photonic elements are integrated in a single millimeters by millimeters photonic integrated circuit. So the photodetectors is not disaggregated, interconnects are not disaggregated, everything is just compact.
So you brought up the number of optical fibers that need to interface with this type of system. I'm going to assume that those are all of your I/Os that you could access on the chip. Is that correct?
Well, an optical engine in general can have many different interfaces. So you may have, let's say, bare optical ports. As you mentioned, this might be coming through optical fibers. Um, or there are many different ways to get into the photonic integrated circuit, but the optical fiber is the conventional one that interacts with the external world. Within a photonic integrated circuit, that incorporates modulators and photodetectors. Another interface that you will have is high-speed RF analog inputs or outputs. If you are enabling also analog-based processing, like for example for microwave photonics applications or RF applications. And at the same time, you may have also digital I/Os. So similar to the ones that you might find on a GPU or a processor in a computer, being able to get digital signals within the device or the system, and then your signals go through a digital to analog converter, and then the analog directly feeding a modulator. So I would say that you may have like three interfaces for a complete photonic engine, both
Okay,
digital, RF, and optical.
I see. Okay. Well, this is all very interesting. We're running a little low on time, but I think for our last question, I'd just like to ask, what do you see as maybe the next generation of these systems? Is it just miniaturization? That's your goal, or do you see it expanding out in kind of the current form factor to a broader array of applications, maybe automotive, maybe aerospace, maybe medical, things like that?
Mhm.
Or is it a combination of these two? Or are you just being driven by customers?
Yeah, I think that the answer is we are driven by customers, but at the same time, of course, we are internally studying where the technology it's going to be able to deliver the next generation performance in some of the fields that you mentioned. We are focusing today on communications space for optical-based communications and management, for RF communications and the processing intra-data center communications. But as you mentioned, there are also many different fields where we actually believe that the photonics and in particular programmable photonics is going to be able to deliver what's it's going to be required next. I think that a common feeling of the applications and protocols that are appearing they have one thing in common, which is the flexibility and the programmability that is required. The world is changing every minute, in terms of technology even more. So what was valid 4 years ago, now it's not valid anymore. The communication needs, the signal processing needs for optical networks is growing at a pace that is much higher than the one that the technology is able to deliver. So it's going to be really interesting to see in the future what are the actual technologies that allows us to keep growing with the same speed that we as a society are growing on many different application fields. We believe that photonics is the actual candidate to complement electronics and boost these kind of applications and even enable these next generations. And we certainly believe that programmable photonics is going to be key in order to being able to put photonics technology in the hands of, of the society.
Well, great. As all of this stuff rolls out, it would be great if we could have you on again in the future to discuss it, because I'm sure it'll be very interesting and people will be eager to hear about it.
Yeah, perfect. Thank you.
Thank you very much for joining us. We've been talking with Daniel Pérez López, co-founder and CTO of iPRONICS. Make sure to check out the show notes for some very interesting resources, and you'll be able to learn more about iPRONICS and their products. If you're watching on YouTube, make sure to hit the subscribe button. You'll be able to keep up with all of our episodes and tutorials as they come out. And last but not least, don't stop learning, stay on track, and we'll see you next time.